It's a pleasure for me to be here and speak in front of such an audience in such a meeting. I'd like to tell you how I got to speak in this meeting. In August, I got a mail from one of our organizers, Carmel, and she described this meeting to me, and she said that in this session there are going to be arguments regarding the similarity between carbon and silicon, which are often raised in the context of possible replications of silicon-based molecules. This is a translation from Hebrew. I hope that I'm doing you just here. And she wrote that we want to have a solid perspective on these matters from an inorganic chemist. Now, I'm an inorganic chemist, but these are not my lines of research. However, at the end of this message, there was also, are you the person we're looking for? I could not resist. No one can resist such an invitation. And this is why I'm here. So, why are we so fascinated with the relationship of carbon and silicon, and in particular silicon-based life? So I find two reasons for that. The first one is that we don't want to be chauvinist. We do not want to be considered as chauvinists, concentrating only on carbon. So when we raise our heads to the skies looking for alternative life forms, we want to look beyond carbon, and silicon is its next of kin. It's the closest family member to carbon. Now this is the periodic table introduced 150 years ago by Mendeleev, in which the elements, the chemical elements, are organized according to their atomic number. From left to right, hydrogen, helium, lithium, beryllium, boron, carbon, and so on and so on. But you see that they're not organized in just one line. They're organized in such a way that this line stops and then a new line begins. And by doing so, elements in the same column belong to a family. Okay? And for instance, on the right-hand side, we see the noble gases, helium, neon, argon, krypton, and so on. And if we look at this row here, we can see that carbon and silicon belong to the same the same column, and therefore we say that they are very closely related. They have some chemical relationship. But this is just one reason. The other reasons for us to be fascinated with silicon-based life is technology, which is the topic of this meeting. And here in this slide, you see a silicon ingot from which we make the wafers, from which we make the microprocessors, from which we make the computers. So the current information technology depends on silicon. And we may think that can silicon-based life forms evolve spontaneously, bypassing the intermediacy of ourselves, of carbon-based life forms, and maybe we would encounter such species. However, when we think about chauvinism, we should consider that chauvinism goes both ways. So for instance, the Nobel Prize for 2016 was given to three chemists, Sauvage, Stoddart, and Feringa, for inventing the molecular machines. These are machines on the nanoscale. We have a nano elevator on the left-hand side and the nano car, which is 1 billion times smaller than the real elevator or the real car. And these are perhaps would constitute some of the future technology, but they're made of carbon. I mean, these researchers could have chosen any element that they wished for, but they chose carbon because this is the most versatile atom in the periodic table. And the second thing is that this is a current technology. Silicon-based technology is current technology, but it is being thought, it is being proposed that future technology may depend on other atoms, not necessarily on silicon. So indium gallium arsenide is proposed as a future technological material. And even carbon-based materials are proposed as future materials. Namely, if you were to hold this conference in 20 years from today, perhaps silicon would have been something of the past. And then we would not need to worry about relationships between silicon, technology, and life, because even technology would be carbon-based. So what are the minimal requirements of a living system? We will refer to this as a self-replicating system, a system, an entity which may produce copies of itself. But this is too broad, because even ideas or computer programs may fall under such definition. So I would like to narrow down this definition to confine it into self-replicating chemical systems, like ourselves. We depend on chemical reactions to reproduce. And then I would like to define it even further, to confine it even further, and say that these life forms need to be liquid-based. And I'll give you explanations for that, why we insist on that. And then it could be molecular, but it doesn't have to be molecular. So why do we require that our living systems, our self-replicating systems, need to be liquid-based? because reaction and physical processes in the solid state would be too slow, and reactions in the gas phase would be too dilute, and not many molecules would go into the gas phase. However, interactions in liquid, the liquid may dissolve different types of species, different types of building blocks, and make them assemble together. This is a convenient medium for smaller molecules, smaller building blocks to assemble to make bigger building blocks. Of course, for us, this liquid is water. And whenever we think about a liquid, we should think about the window of temperatures. Beyond 100 degrees, it would become a gas. Below 100 degrees, it would become a solid. So we have some window with which we can produce lives. So this liquid dependence, from my perspective, from other people's perspective, is a good criterion for distinguishing between the natural and the artificial. And we can use this as a demonstration. Let's suppose that we're Dorothy and we're brought from our homes in Kansas into some magical world in which we encounter different species. And these species are the scarecrow, the tin man, and the cowardly lion. And now, as a evolutionary biologist, Dorothy needs to distinguish which of those is natural and which of them is artificial. Now, the scarecrow is solid-state technology. This is solid, and the tin man is solid-state technology. There's no liquid in them. However, the cowardly lion is just like any other lion. It is full of liquid, and therefore, this is supposedly, the lion is supposedly an entity that could have evolved by a stepwise process, whereas the solid-state creatures need to be artificial. And if we encounter during our lives such a creature, and you can tell the resemblance between the tin man and this robot type, then this is also artificial. This would not have been a naturally evolving species. And how do we imagine an evolutionary process? We imagine a prebiotic world, a world in which the species were not still involved in replication. And this world was full of building blocks, small molecules. And according to Darwin, this world consisted of some warm little pond, this primordial soup. And these small building blocks assembled together via recognition and assembly and replication to form more complicated molecules, more complicated entities, which with natural selection and further replication gave rise to more complicated entities, and ending up with, for instance, our cells. And this is the Miller-Urey experiment, which was supposed to produce this primordial soup, this small little pond. In this experiment, water vapor and some gases which were supposed to represent the original atmosphere, methane and ammonia and hydrogen, were ignited with sparks. And this process repeated again and again for 1 week. And then the soup that formed was analyzed. At that time, it was analyzed in a primitive way, but even when we analyze it today, we see that this soup that is forming is full of amino acids, the basic molecules from which life is constituted. So we know that this pond can form, but can it also be the beginning of life? So we can also imagine some other forms of beginnings, not necessarily molecules, but also crystals. Now, crystals are different from molecules. Molecules may contain 2 atoms, 1,000 atoms, 100,000 atoms, but these would be individual entities. Crystals they could have a small number of repeat units, let's say only silicon and oxygen, only carbon and oxygen and sodium. However, the numbers of the individual atoms is huge. These would be billions and billions of atoms. And crystals have a specific property. These units, these building blocks are organized in a periodic pattern, a repeat unit. Okay, and we can think that crystals could also represent some sort of life, because crystals are not considered to be living, but embedding a crystal, let's say sodium chloride, salt, within a saturated solution of sodium chloride, we'll have new crystals forming. So we have some sort of replication. This is not really life, but this is replication. And then came the hypothesis in 1966, which got me and yourselves into this problem, the Karen-Smith hypothesis, that said that crystals may be regarded as genes, because this pattern may change. So let's say that we have a crystal in which the pattern of the repeat unit is not identical to its parent. and then new crystals would grow, which would inherit this chain, and then newer and newer daughter crystals would grow, and therefore we'll have some pattern, which is like a computer card from the old days. And this could, on such crystals, life could begin. And particularly, he said that these crystals could be clay, and clay contains silicon. So here is the connection between silicon and carbon. I should say that Karen Smith, who died earlier this year, this theory is mostly ridiculed. Most people would not take it too seriously, but it might be correct. So this is a short history of chemistry. Historically, chemistry was divided into 4 subdisciplines: organic, inorganic, physical, and analytical chemistry. And for us, the most important is organic chemistry. Now, originally, it was thought that organic compounds, which make the organic chemistry, could only be prepared by living species. There was some sort of vitalism into organic chemistry, and therefore they could not be synthesized in the lab. But about 200 years ago, an experiment by Wöhler showed that you can make ammonia. And ever since then, we can make these molecules, which originate from in the living world. We can now make them in the laboratory. And now the definition is a bit more diffuse. It could be a compound that contains carbon-carbon bonds or carbon-hydrogen bonds, and so on. But in any rate, these are compounds that contain the element carbon. And therefore, we say that life, as we know it, is regarded as carbon-based. Okay? And we go on from there. And I would not give you a lesson in chemistry, but what I would like to do is to impress you with the diversity of the structures of organic compounds. So what we see here on this slide is a nucleotide, a glucose, amino acid, phospholipid, and ATP. Now all these compounds contain carbon, but we sometimes use a shorthand. So for the amino acid, carbon is symbolized by C. So this is carbon and hydrogen, nitrogen, and oxygen, and so on. So this is a more specific way of writing organic compounds, but in some cases this is too detailed for us chemists. So what we're doing is we're using shorthand. So every junction here represents also a carbon atom. So it's carbon bound to carbon, to carbon, to carbon, to carbon. We have 5 carbons in a row. And here we have 6 carbons in a row. 1, 2, 3, 4, 5, 6. Okay, so this is typical of organic compounds. And these specific organic compounds serve as building blocks for more elaborate structures. So for example, the phospholipids are used for making the cell membranes in the body of every living organism. They are arranged together in a so-called fluid mosaic. And glucose, which we know from nutrition, is also used for making cellulose, which is a strong structural material used for keeping the sequoia trees 100 meters tall without breaking. And amino acids are used for making peptides, short peptides, but also proteins. In this case, we do not write the exact character of every atom. We just distinguish these amino acids by codes. So we have 2 types of amino acids in this molecule, which is insulin. And of course, the nucleotides are building blocks made for making DNA, the so-called immortal coil. So we have this carbon sugar phosphate backbone of this oxygen binding to this sugar, and then we form a huge string of repeat units which wrap around each other in a helical manner, which stays alive forever. So when we die, our DNA lives after us. So these are all very exciting parts of the organic world. But there are also other types of organic molecules. So morphine is a very complicated organic molecule, and Taxol is an extremely complicated organic molecule, and mitotoxin is an unbelievably complicated organic molecule. All of these have these carbon-carbon bonds, carbon-hydrogen bonds. They are very, very complicated molecules. And there are also examples for so-called non-organic molecules. For instance, carbon dioxide is considered inorganic. It contains carbon, but it is not part of the organic group of molecules. Now let's look at the essential elements. So this is taken from Wikipedia, and this would be our body, and we see that oxygen and hydrogen are very high concentration. This is by weight, not by atom number. But oxygen and hydrogen exist in large proportions because most of our body is water. If we exclude this water, we see that the next atom in line is carbon. And we see many of those, so carbon is the most abundant element in our body, and then we can see nitrogen, calcium, potassium, sulfur, chlorine, and magnesium. We can also see that silicon is absent. Silicon is not a vital element. It does exist. It may exist in our body as a trace element, but it's not important for the function of our bodies. And when we compare this to the abundance of the elements on the crust of the Earth, we see a huge difference, because on the crust of the Earth, silicon is the second most abundant atom. It is 1,000 times more abundant than carbon. So in our bodies we do not see silicon, but in the inorganic world, in the crust of the Earth, we see a lot of silicon. Maybe it tells us something. So silicon on Earth, there are several reasons for that. One of them is that silicon on the face of the Earth is abundant, but it is not necessarily accessible, and we should differentiate between these two functions. It is on the face of the Earth, but it is locked in minerals, which most of them are insoluble. This is one of those minerals. This is topaz. This is a form of silica, a form of quartz, a form of silicon dioxide, and this is as it is found naturally, and this is after it is made into a gem. So this is one of the silicon-based minerals. But of course, we do not need to worry about what is happening on the crust of the Earth, because I've just told you that we should be interested in the water, because we think that life originated from water. So the dry part of the Earth is less important. And when we look at the oceans, we do see that carbon is now more abundant than silicon. But this is an accessible form of silicon, because it is already dissolved in the water of the oceans. So silicon does exist. Carbon is 30 times more abundant than silicon, but silicon does exist, and to some appreciable amounts, because other atoms which are used by the body, for instance, nitrogen and phosphorus, which are essential elements, their concentrations in the water is even lower than that of silicon. So silicon does exist. So is it only a matter of availability, or does it go beyond that silicon does not, we do not see much silicon in our bodies? And the question is, has nature learned to exploit silicon? And the answer is yes. So these are diatoms. These are marine organisms, biological phytoplankton, and this is their top structure and their side structure. They are very symmetric, beautiful to the eye. They are microscopic. Their size is about 1 micron, but this skeleton is made out of silicon. So this is a very nice form of silicon, but silicon in nature, in diatoms or in other organisms, only plays a structural part. It does not play the same part that carbon plays as we do in the DNA and in the other functions. So what is so special about carbon? This is the periodic table again, and the latest periodic table, but we want to concentrate on the lighter atoms. There are about 100 atoms here. We want to concentrate on the lighter ones, the ones which are more relevant to us. So let's erase some of these atoms. There are some chemists in the audience that I hope they will be able to forgive me for what I'm doing. And then what we'll do now is join together the two parts of the periodic table. So these are the 18 first elements joined together, okay, in their order. Hydrogen and helium, and then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, and then nitrogen and say sodium, and so on. So what is so typical about carbon? What makes carbon such a great element on which life can be based? Sorry. It has the best seat in the house. Carbon is in the middle of the first row, from which it can do all its functions. Now, what do we mean chemically when we make such a claim? What we mean is that carbon has intermediate properties, electronic properties. So this intermediacy enables carbon to form stable bonds both with electron withdrawing elements to the right of it, like oxygen and nitrogen, and electron donating elements like hydrogen, which is to the left of it. But most importantly, it can form stable bonds with itself. So this carbon-carbon bonds that you've seen on my earlier slides are possible for carbon, but they're not so much possible for silicon. So how similar are carbon and silicon? So one of the principles in the periodic table is that this similarity along a column. So since carbon and silicon belong to this same column, they're similar to each other. But there are other traits in the periodic table which are not so apparent. One of them is the uniqueness principle. And this one says that the elements of this row, starting with lithium and containing carbon, are different from all the rest of the elements. So silicon is similar to carbon, but not so much as we might expect. So these elements are unique. And in addition, there's another trait which is called the diagonal relationship, which says that for some of the traits, there's similarities along the diagonal rather than along the column. So silicon has some resemblance actually to boron more than it does to carbon. And when we look at the more detailed form of the periodic table, now with some color codes, we can see that carbon is a non-metal, whereas silicon is a metalloid, and it's closer in some respect to boron rather than carbon. Namely, what we're saying is that next of kin, close relatives, are similar, but not necessarily identical to each other. And we can demonstrate this by looking at carbon dioxide versus silicon dioxide. So apparently these are two very similar compounds, but carbon dioxide is a gas. It has two double bonds between the carbon and the oxygen, whereas the silicon has 4 single bonds between each silicon and the 4 neighboring oxygen atoms, which make it a solid. So one of them is a gas, the other one is a solid. One of them can participate in life, one of them is stuck in rock. And I would like to say that silicon does have various applications, and we, for instance, high temperature resistant cookware, and silicon adhesive and other more kinky applications of silicon, which I was seriously advised not to use in my lecture, so I would not mention them, but there are other applications of silicon. So silicon chemistry is rich, but all of this is synthetic chemistry. This is not natural chemistry. We can do it in the lab. We do not find any equivalence of that in life. So what I want to say, I'm reaching the end of my talk, but what I want to say is that biological, natural systems are based on such building blocks, carbon-based building blocks, and this is liquid technology. So whenever we encounter liquid technology, we know that this could be it might be biological, it might be life. And this is graphene on the right-hand side, which may lead to those machines that eventually might inherit the Earth. And this is based on carbon. So we have carbon on the left-hand side, we have carbon on the right-hand side, but there is no real connection between this carbon and this carbon. There's no evolution that we can think of, that I could think of, that would lead from this liquid-based technology to the solid-based technology on the right-hand side. Now, we may now go to silicon and say that maybe life did emerge with these clay crystals as proposed by Karen Smith that have later led to this, on which the carbon-based molecules assemble and so on. But this still doesn't get us closer from this early stages of the evolution to the current solid-state technology. We're no closer by coming up with this hypothesis. So I have some epilogue as well. I do have another 5 minutes, right? So I'll summarize this part of my talk by saying that we still do not know what the original replicators looked like. If they were molecular, they could have been, they should have been, they probably would have been carbon-based. And if they were based on crystals, then possibly, if Karen Smith's hypothesis is correct, then they could possibly be silicon-based. But anyway, very early in the evolutionary ladder, replication was carbon-based. And when we crawled out of the water, we were carbon-based. And when we came down from the trees, we were carbon-based. And we're currently depositing our souls away to the hands, to the minds of silicon-based machines, but possibly in the future, the machines that would eventually inherit the Earth would also be carbon-based. And so this is the summary of my talk, but I would also like to tell you about things which are closer to me as a chemist, and this is the following. What about indeed other types of alternative life forms? And I only talked about carbon versus silicon, but of course you can talk about systems that rely on different liquids, for instance, ammonia or methane or hydrogen fluoride, and the chemistry that would be involved with it would be quite difficult, quite different. But I want to talk about another aspect of alternative life forms, and this is the one which is easiest to imagine and the one that perhaps would be most probable, and these are the relationship between mirror images. So an object which is not superimposable on its mirror image is termed a chiral object. This is the definition. This comes from Latin, apparently. So for example, two gloves One of them is the mirror image of the other. They're not identical, they're not superimposable. They look alike, but they're not superimposable, and therefore they are regarded as chiral objects. My hands are chiral objects because my right hand is not superimposable on my left hand. And as it turns out, the building blocks, some of which I've shown you earlier, on which the living species are based, they are all chiral. All the amino acids, except for glycine, 19 out of the 20 amino acids are chiral. So this is an important part of the living world. And moreover, the living world includes only one of those enantiomers, only one of those gloves, only one of those hands. All the amino acids are air, not a mixture of the two gloves, let's say, but only one of them. Nature has chosen to use only one for clear evolutionary reasons. So nature is built on one of those. The two in the original Miller-Urey experiment, in which methane and ammonia and hydrogen and water were combined, these two species were formed. But when evolution occurred, it relied on only one of those possibilities. And one of the questions which is still intriguing evolutionary chemists and biologists is how was a specific enantiomer chosen from the mixture of the two? Okay? The mixture is available, only one of them is being used. It doesn't make any difference which one, but only one. How can one be used and the other one be neglected? And in the context of the present conference, could life evolve relying on the opposite enantiomer? Okay, so this is one possibility, and this is the other possibility. There might be life which took advantage on the other possibility, on the other glove. And if we were to meet such a mirror image creature, how would we interact with one another? So there are different ways of describing these two mirror images. One of them is L and D. One enantiomer, one glove would be termed L, and the other one would be termed D. For instance, alanine, there are two enantiomers, two mirror images. One of them would be termed alanine, and the other one would be termed D-alanine. But a joke that has been going on in the net for some time is that Samuel L. Jackson is actually one of those creatures, and perhaps in some other part of the universe there is Samuel D. Jackson as well. And so perhaps these enantiomeric forms in the other part of the universe do exist. And my question is to you, I'm joining the chairman, hopefully we won't turn our backs into each other when we do meet. Thank you.